All right, guys. Hi, it's Miss Edwards. We're going to go ahead and start. So go ahead and pause the video and see if you guys can figure out the warm-up questions. And when you're ready, unpause. All right, so there was 4 different types of transformations that we've talked about. The first one is represented by the red box, and that is a translation. Okay, the blue one is a turn or a rotation. The green one is a flip or a reflection. And our last one in purple is the most recent one we talked about a couple weeks ago, and it is a glide reflection. Okay, and a glide reflection basically is a combination of a reflection and a translation together. So you're sliding and reflecting in order to do a glide reflection. So these are the 4 different types of transformations we talked about. These are rigid motions. Okay, so rigid motions are those ones that it's still the same size, still the same shape, just maybe in a different orientation or maybe reflected and whatnot. Okay, so rigid means stiff, stays the same. Okay, and then the ones that we talked about on Friday were dilations. Dilations are not rigid because they are going to change the size and shape of our item. Actually, just the size. The shape will stay the same. Okay, so in today's lesson, we're going to use dilations and rigid transformations to determine if objects are similar. So if you guys remember, we talked about congruent. Oops, sorry. Okay, using this symbol, and congruent means they are identical, they're exactly the same. So we're not talking about that today. Today we're talking about similar, which is represented just by the squiggle, to see if a transformation creates similar figures. Okay, so our first one, graph a composition of a rigid motion and a dilation. So just as a reminder, let's take a look at the notation on this. If line M is represented by the equation x equals -3, what is a graph of the image? And then we have this notation here. So what this means is the first part tells us what's happening. We're reflecting, because I see that big R over line M. And then we have that circle in the middle, which means after. D stands for dilation. And then I see 0.5 there, which tells me.
Mark, to the office, please. Mark, please come to the office. Thank you.
Sorry. The 0.5 tells me this is going to be a reduction. We're going to have a scale factor of 1/2. Okay. And then the triangle ABC part just tells us what are we reflecting and dilating. Okay. So according to this, it means we're going to reflect over line M after we dilate with a scale factor of 1/2. So very first thing we need to do is we need to dilate with a scale factor of 1/2. So we're going to dilate first. Okay, that is the trickiest part, figuring out which one you're going to do first and which one you're going to do second. Okay, so if we dilate this with a scale factor of 1/2, we can either multiply by 1/2 or 0.5, or we can divide the numbers by 2. So what I'm going to do first is I'm going to take all of my ordered pairs A, B, and C, and we're going to divide all those numbers by 2. So go ahead and pause the video if you would like. Divide all your numbers by 2 and tell me what A prime, B prime, and C prime are. Okay, I'm going to go ahead and fill these in. Okay, so that's what I got. If I go ahead and I graph them onto my graph here, I'm going to just graph those ordered pairs. 1, 2, that becomes A prime. -1, 4. B prime. And then 0, 5 is C prime. And then we can go ahead and take a look if we were to connect those dots. You'll notice I have the same exact shape, just a different size. It's half the size of the original. Okay, So technically I've done one of those two different transformations. I've dilated. Now I need to reflect. So if we look at the next slide, this is what it looks like in your book. The same thing I just showed earlier that I drew, the dilation. Okay, so we check that off. We dilated. Now we have to reflect over line M. If you remember line M, it says is x equals -3. So I'm just going to take my line here and I'm going to go ahead and put a line at -3. Okay, that is my line of reflection. And we can simply count how far away is each one of my order pairs in the primes away from the line. Okay, so it looks like if I start here at B prime is 2 spaces away. So I'm going to go on the other side, and then now it's going to be B double prime. Okay, and then C prime, it is 3 spaces away. Actually, let me see if I can move my B prime so that way it doesn't get in the way of C prime. Okay, C prime is 3 spaces away. So 3 spaces away over here is C double prime. And then A prime is 4 spaces away. So that would be here, A double prime. And then I can see my shape. Okay. And then if you think about the ordered pairs of that, if you want to write those down, the ordered pairs of my shape should now be -7, 2, -5, 4, and -6, 5. Okay, so we completed 2 rigid motions. Okay, well, actually 1 rigid motion. We completed the dilation, which is not rigid, but then the second part was rigid because we went from the primes to the double primes by doing a reflection. Okay, so we're going to figure out, was this similar? So is the shape the same? Yes. Is the size the same? No. So technically, these are similar. It's a similar transformation. Okay, so this is the same thing again. It just shows both of them. And then look at the conclusion part here. The graph of the image, reflection over line M after dilation of 0.5 for ABC is triangle A prime, B prime, C prime. So that's how we note it. This is called a similarity statement. And you're going to see this again in a couple minutes. Okay, because they are similar. Okay, so here is a try it. So I want you to go ahead and pause the video, see if you can answer the questions and graph them. All right, let's take a look at this one. Okay, and I will tell you the very first time I did this on my notes, I did not follow the directions because I didn't pay attention to the order. So it's really important that you think about what goes first and what does that notation mean, because that is guaranteed to be the place where people mess up on the test, is not reading the notation correctly and therefore not graphing it correctly. So what does that mean? Dilate with a scale factor of 2 after translating. And if you remember the translation notation, 1 means 1 to the right, and then -2 means down 2. Okay, and then we're going to be doing that to triangle XYZ. Okay, so you can say, as far as what does it mean, dilates after translating. Or after translating. Okay, so what do we have to do first? The very first thing we should be doing is we should be translating. Okay, and I knew right away that I did something wrong when I did it incorrectly, because I started dilating and I'm like, wait a minute, this goes way off my graph. Why would they give me a graph and it doesn't fit? So that was an indication, hey, I need to go back and I need to look and see what I did wrong. Okay, so I'm going to translate. So again, 1 right, down 2. So every single point is going to move the same distance in the same direction. So 1 right, down 2. That puts me there for Y. So that becomes Y prime. And the ordered pair for Y prime is 0, 2. Sorry, 0, yeah, 0, 2. Okay. All right, if I move my X one right down 2, that'll put me here for X prime. Okay, and that new ordered pair is 4, 3. And if I do the same thing with Z, right 1 down 2, I have Z prime, and that ordered pair is 2, 5. So you could either do it just by using your graph moving, or we also talked about how you can take each ordered pair, add 1 to the X value, subtract 2 from the Y value. So you can do this without the graph too. All right, so here's my translation. Let me go ahead and connect the dots just so we can see our triangle. It's always good to do this because then I can see, yep, it still stayed the same size, still the same shape. So I'm good as far as the translation goes. Okay. All right, there's the thing. I just expanded it a little bit, give us a little bit more graph to work with because we are going to dilate this. We're going to make it bigger because it has a scale factor of 2. So now I checked off translation because we did that. Now we have to dilate. Okay, dilate with a scale factor of 2. Okay, so what we're going to do is make sure we're taking our prime ordered pairs, so the ones that are listed in red, and we're going to multiply every single number by 2. Okay, so when it comes to our X1, we have 4, 3, so that's going to become 8, 6. Our Y is 0, 2, so that's going to become 0, 4. And our Z is 2, 5, which is going to become 4, 10. Go ahead and pause the video, graph it, and then we're going to unpause to see if yours matches mine. Okay. All right. 8, 6. X double prime, because this is our second transformation. 0, 4 is our Y double prime, and then 4, 10. 4, 10 is up here. That's our Z double prime. And again, I'm going to go ahead and connect my dots. Okay. And I can see it's still the same shape, but it's a different size. So my original in black and my one in blue, they're similar, but they are not congruent. This is not a congruent transformation. It is a similar transformation. Okay, when you hear congruent transformation, that's the same thing as when we're talking about rigid motion or whatever. Okay. All right, let's go ahead and get that box out of the way, make it a little bit easier for us to see. Or we're just going to click on everything. Let's try one more thing. Okay, so this time it's the same image, just blown up. The red triangle was the one after we did what operation or what kind of transformation. Red one was our translation. Okay, the blue triangle was what we did after our dilation. Many times I see students trying to jump from the black one to the blue one immediately without doing that step in between. Technically, you could do it that way, but you're more likely to make a mistake than if you show all 3 steps. So you can do this with different colors if you would like, but making sure that you have those primes and double primes on there are key. Okay, there's color pencils on the card if you would like to use different colors. All right, so our next one, we're going to describe a composition of rigid motion and a dilation. Okay, is there a composition of transformations that maps XYZ onto JKL? Explain. Okay, so looking at these, let's answer these questions that'll help us answer that. The 2 triangles appear to be the same blank, but different blank. They appear to be the same shape, but different sizes. Okay, since the pre-image, which is the one in black, is in quadrant 1, and the image, which is in red, is in quadrant 3, what type of transformation do you think happened? Yeah, it was a rotation. Or rotated. Okay, but that's the only way we can really get it from one to another if we rotate it. Okay, it looks like it was rotated counterclockwise. And how many degrees does it appear to be turned? It looks like it would be 2 turns if we're using patty paper. So that's 180 degrees. Okay, since JKL is larger than XYZ, that what other transformation had to have happened to make it bigger? It had to have been dilated. And we can always figure that out. If you're looking up here, I always try to find a vertical or horizontal line. I can tell by looking at the original, this side is 2 wide. The one that is corresponding to it would be this side here, and that's 4 wide. So 4 is double 2, so therefore our scale factor was 2. So dilated by 2. Okay, the reason why this question is important is because you have to be able to look at a transformation or a series of transformations like this and pick out exactly what happened to it. Okay, if you're struggling with this and you can't figure out how to go from one to another, what I suggest doing is to use patty paper, because that'll help you figure out if it was a rotation, a translation, or a reflection. And then once you get to that point, you know if it's bigger or smaller, it had to have been a dilation. Okay, so we talked about this already. We said that it was 180 degrees about the origin. And remember, if it's about the origin, that's automatically counterclockwise. Okay, so they just want us to list the ordered pairs for this. So in this one, it skipped the middle step. Okay, so it went from the black to the green, which is not there, to the red. So let's see if we can help do this a little bit. Without having patty paper, remember, we can follow the rules of rotation. If you remember, for 180 degrees in either direction, if you take the opposite of X and the opposite of your Y, that's going to give you your ordered pairs. Okay, so go ahead and pause the video. I want you to think about the ordered pairs for X, Y, and Z, and then apply that rule to show me what X prime, Y prime, and Z prime would be. Okay, so you should have had -2, -1. Sorry, it's parenthesis. -1, -4, -4, -1. Okay, and then now we have to perform the dilation. We have to do it by a scale factor of 2. Okay, and you can always tell, this is a good way if you're not sure just by looking at the graph. If I write down the ordered pairs of J, K, and L, which are -4, -2, -2, -8, and -8, -2, you can kind of see how did you go from -2 to -4? Well, that's times 2. And -1 to -2, that's also times 2. And you'll notice that all of them are scale factor of 2. You have to multiply them all by 2 to get to one from the other. Okay. All right. So this one, I'm just going to talk about the top part, and then we're going to look at this little cartoon that's on here. So the top one, this was the one that we were talking about being rotated, whatnot. Do you think your answer holds true for all compositions or transformations? And I want you to look down here. No, if you translate and then rotate about the origin, the result is different than if you rotate and then perform the translation. Okay, so that's going to give you different results. And that's why I really like this cartoon. You know, it's customary to put the heavier stuff in first at the grocery store. And then the girl says, what's the difference? Okay, so if you put in all your light stuff like your bread and your eggs in the bottom of your bag, and then you shove in the heavy stuff like a gallon of milk and, you know, a 2-liter soda on top, what's going to happen to your eggs and your milk? Sorry, your eggs and your bread? They're going to get crushed. So the order does matter. Okay, can you think of any other time, either in life or in math, where order matters? Okay, well, I think about when you get dressed. Okay, when you get dressed, don't you put your underwear on first and then you put your pants on, right? If you did it out of order, you'd be looking funny walking around with your underwear on the outside of your pants. Okay, or if I think about math operations, if I have 10 of something and I add 2, and then I go to divide by 2, I'm going to get different results. 10 plus 2 is 12. 12 divided by 2 is 6. If I did it the other way around, 10 divided by 2 is 5. But then if I add 2 to 5, I get 7. So I get different results by adding and dividing if I do them in opposite orders. Okay, so the same concept applies to when you're doing transformations. Rotations and translating is different than translating and rotating. All right, so this one is finding similarity transformations. Why is PQRS similar to JKJH? Okay. A similarity transformation is a composition of one or more rigid motions and a dilation. A similarity transformation results in an image that is similar to the pre-image. Okay, again, we talked about similar being the same shape, different size. Okay, and then let's talk about the differences a little bit. This one can be a little bit different because of what it preserves. The difference between a rigid motion and a similarity transformation is a rigid motion preserves distance and angle measure. Okay, and then you can also say it also preserves the side length. I'm going to put that on there too in parentheses. If I were to take a parallelogram and I were to do one of those rigid motions, a rotation, a reflection, or a slide, it's still, the side lengths are going to stay the same. So are all the angles, everything's going to stay the same. Okay, they're congruent. Similarity preserves angle measure, but not the side length. Okay, it's still going to be the same shape, it's just going to be different sizes. All right, here are some properties that we need to talk about when it comes to similarity. Okay, the reflexive property we talked about before. Something is congruent to itself. This one's just A is similar to A. Okay, it's similar to itself. The symmetric property, think of symmetric is like a reflection almost. If A is similar to B, then B is similar to A. It comes back at you. It reflects back at you. That's kind of how symmetric works. They're very similar, reflexive and symmetric. Transitive, this is that one we've talked about before. If A is similar to B, B is similar to C, therefore A is similar to C. So it's our three parties there. Okay, and there will be ones that I will provide for you if you need to use them in a proof. Okay, let's see if we can try this one. Okay, describe the possible similarity transformations for a pair of similar figures shown and then write the similarity statement. So go ahead and pause the video. I want you to talk amongst yourselves and see if you can figure out what three different transformations could we do to get ABC to land on top of A prime, B prime, and C prime. All right, so you definitely have to rotate. After you rotate, you might have to translate a little bit. Okay, and if I had patty paper, I could rotate it and then I might have to slide it down a little bit. And then after I do that, then I would have to dilate it because it appears that the ABC primes are slightly bigger than the A, B, and C, sorry. Okay, as far as the similarity statements, our first triangle, we could say triangle ABC is similar, and then I have to match up part for part. Okay, what is the A similar to? A is similar to A prime, B is similar to B prime, and C is similar to C prime. So you have to make sure that the order of your letters match. Okay, let's double check. It's exactly what they have on there. Okay. All right, see if you can try this one. This one only has two transformations this time. So the very first thing is I see the orientation is different. I see X, W, Z, Y, but then if I look at the bottom, it's X, Y, Z, W. So the orientation clockwise has changed. So that means that I have to do a reflection. Okay, so I need to flip it up because the original is the black one, the red is our new one. So our pre-image is reflected up. And then we have to dilate. And this is going to be a reduction because the original is bigger than the new one. Okay, similarity statement. We have WXYZ is similar to W prime, X prime, Y prime, and Z prime. Okay, these should be pretty easy because the letters typically match up with their primes. The only thing is sometimes it gets tricky because as we saw earlier in this lesson, they had like X, Y, Z, and then they had different letters in the new figure. All right, this one here, determine whether it is similar. So an artist copy her sketch to cover an entire wall, measuring 15 feet high by 20 feet wide, so her mural can be similar to her sketch. Okay, so for anybody that is an artist, you would definitely know what this one's talking about. We want to make big, make it fill a whole wall. Okay, the only thing we have to think about is we need to make sure that it's proportional because as we talked about in our lesson on Friday, if you don't do it proportionally, what's going to happen to the mural? It's not going to look right. It's going to look warped and stretched. Okay, so one of the things that we definitely have to make sure is this little hit right here. We need to make sure that our units are the same. Because if you notice in the picture, the sketch is in inches and then the wall is in feet. So that's the very first thing that I want to do is I want to convert them to be the same. I'm going to convert my wall into inches. Okay, so this is the wall ones. Okay, so if I have 15 feet, how many inches are in a foot? There's 12 inches. So I have to take 15 and multiply it by 12. And that gives me 180 inches. Okay, my 20 feet, I multiply that by 12, then I get 240 inches. So now I'm going to use these numbers instead because they are the ones that are similar to the other one. Now we need to figure out the scale factor. Okay, so let's talk about it. The sketch was 11 inches by 14 inches. Okay, the wall we now know is 180 inches by 240 inches. Okay, so how can I go from 11 to 180? Well, you can actually divide. If I divide 180 by 11, I get 16.36. Okay, what happens if I divide 240 by 14? Okay, let's try that. I didn't try that one on mine. Here's my calculator. 240 divided by 14. I get roughly 17.14. So that's not going to work. The proportions are not the same. So this is not going to work. It's not going to look right when she puts it on the wall. So those proportions are not the same. Okay. All right. So let's go ahead and summarize this a little bit. Okay. In words, a similarity transformation is a composition of one or more rigid motions and a dilation. Two figures are similar if their similarity transformation maps one onto the other. And then this is one, we haven't talked about circles yet. We will in our next unit. All circles are similar to each other. Okay. And then in the diagrams, you can see they have a triangle that's been dilated and rotated. And it shows that these two triangles are similar. And then, backwards, looking backwards, it says ABC to XYZ. It's been rotated, then dilated. And then this one shows two circles that are similar. All right, for this one, there is only a few questions. There's 3 questions from the book that match up with your assessment. So go ahead and pause the video. I would like you guys to try these 3. Unpause it, check your answers, and then when you're done everything, if there's anything in the bin that you need to work on, you can work on that. Just make sure you put it back in the bin before you leave. Okay, so this one here, how are similarity transformations and congruence transformations alike, and how are they different? So what are they alike? They both show the relationship after transformations. Okay, so I'm not going to write that one. I'll just say it one more time. Both show relationships between figures after transformations. Okay, how are they different? Similarities include dilations, but congruent ones do not. Okay, similarity include dilations, but congruent figures do not. All right, and our final two, we just had to look at the figures and tell, are they similar? Okay, remember, if they are, you can map one onto the other doing one of those transformations, and it should include a dilation. Okay, for the first one, this one is, yes, it is similar. And it looks like it's been dilated roughly by 1/2, and then it's been rotated. Okay. Now, if you look at number 23, this one is a no. Okay, they are not the same shape. Although they're both trapezoids, you can tell the proportions are just not right. Okay, if I enlarge that top one, the leg should still be shorter than, or like the height should be shorter than the entire thing. So this one is not proportional. There's nothing that's going to map one onto the other. So it is not a similarity. Okay. All right. So like I said, if you are all finished this, go ahead and do anything from the bin. Make sure you put everything back before you go. Hopefully I will see you tomorrow in class. If not, there will be a video waiting for you. All right. Have a great day, guys.